Now, understanding the basic physical characterization and behavior of an inductor, let's try to see how we would analyze the inductor in a circuit. And this is going to lead us actually to a slightly, a nice variation actually on Kirchhoff's second law. Now, the new second law that we've already seen, and we're actually going to take it one step further, in terms of rearranging it, says that the sum of the voltages around any closed loop is equal to not the zero we've traditionally been taught to expect, but now it's equal to, if there are changes in magnetic flux, we have to amend it with the addition of the time derivative there of the magnetic flux. And in terms of inductors, we've just learned that in fact that magnetic flux in general is just directly proportional to the current through the inductor, with that proportionality constant being L, the inductance. Now this is a familiar way of writing down the equation, and in fact, since this L is just a constant with respect to time that just characterizes the solenoid, I can pull that out of the derivative. So this is often written as L times the time derivative of the current, di dt. But there's a very handy mnemonic that electrical engineers love to use, and I think it's very useful for us. Strictly speaking, of course, we have to remember that we're doing sum of voltages equals the derivative of some flux. But we can rearrange this in a very clever mnemonic to make it look as much as possible as the original Kirchhoff's law. The original second Kirchhoff's law, recall, said that 0 was equal to the sum of the voltages around a loop. And I can come to a very similar equation if I simply move this term onto the other side of my equation and subtract it from both sides. So 0 is the sum of the voltages around the loop minus L times di dt. And what's nice about this particular form is, notice, it looks like I'm adding up voltages around my loop for every single element, and there's an additional term that acts like a voltage. It's an effective voltage that corresponds to the behavior of the inductor. So we can rewrite this as, I like to call it, the effective second Kirchhoff's law. That's why I'm putting it in quotation marks, where we say 0 is always equal to the sum of the effective voltages around a loop. And when we write this, of course, all of the voltages that are real voltages that we're used to around the loop, of course, are just still their same familiar form, Q over C for a capacitor, IR for a resistor. But now there's one additional new type of circuit element, and we have to keep in mind that the effective voltage that's associated with an inductor, it's not a real voltage. The real voltage through there is 0 as we go through the wire, right? But in terms of writing down something that looks like Kirchhoff's law, we can effectively take into account the magnetic flux by assigning a particular effective voltage to the inductor, which has the value of minus L times di dt. Now, that's kind of neat, because that looks a lot, in fact, like what we typically write down for a resistor. If we go along the direction of the current through a resistor, we have a minus I times some constant R for the resistance. In this case, it's not I, it's di dt, because it's a time derivative flux where these things come from, times some constant, now the inductance L, instead of the resistance R. And the only thing we need is some kind of a mnemonic to help us track this minus sign. Now, if you think carefully about the sign conventions we established, it went something like this. What we had done is we had our coil. I'm going to try to draw a coil here, right? And what we were doing was we presumed the current I was flowing in a particular direction through that coil. From that determined for us the direction of the actual magnetic field that would flow through there. And then we determined on top of that what the magnetic flux would be, as long as we actually looped through the wire in the same direction we were presuming that the current flowed. So we should get a minus sign in our equation. We've been very careful here tracking our signs if we're going through this circuit element in the same direction as the current. What that means then is if we agree, just like we do with resistors, that's what makes this mnemonic so useful, just like we do with resistors. If we agree to assign a positive sign to the upstream side of the inductor, upstream relative to presumed direction of current flow, and minus as the presumed downstream side, again, it lines up just exactly the same way you would do a resistor. If you do that, then if you're looping through the circuit in the same direction as the current, namely going from the plus toward the minus, that would mnemonically, just like a resistor, sound like a drop in voltage, so you would associate going from that upstream side to the downstream side with a negative sign. On the other hand, if you were doing some Kirchhoff loop and were going in the other direction, from the minus to the plus, of course, you would have to flip your sign, and then once you flip that sign, going from a minus to a plus, you would realize, oh, the term should enter with a plus sign. So the bottom line is, if you just treat it like you do a resistor in terms of deciding the plus or minus that goes in front here, if you do that with that mnemonic, you will always obtain the correct sign. So let me write this actually just like I say, V is not IR, V is plus or minus IR. Well, the same story is true here. This choice of sign is determined by this standard mnemonic. So let me just note that choice of sign is determined by how I've given that diagram to you.